We want to look now at Surds, which is something you've done in the junior school. And we just really this is just a review, but the idea of Surds is to write things exactly in this course. Now, we don't like decimal approximations so much. And what do we mean by that? Well, hopefully you know what a surd as an irrational number, and written in this form where you've got the square root of a number. And what is a square root of a number? It's basically the situation where you could square it and get back to the original number. Now, as we said, surds we want to write as an exact value. So something like the square root of 15. We can't write that any other way as an exact number. If I took the square root of it, I'd get 3.8, 3.9, something like that. But it would be in a decimal that would go on forever, not stop. Like pi and other irrational numbers, they don't recur, they don't have a pattern, they just keep going on forever and never stop. So we can't write it as a fraction, like as a decimal in that way, or get it towards a fraction, because it just doesn't work. So that's what we mean by exact value. Leaving it as an exact value, we'd write it as the square root of 15. So, some properties that we've faced before. Well, multiplication of two surds, well, that's pretty easy. This multiplication and division are not too bad, because you could just multiply two numbers under the surds, put them together and multiply them. That's not a problem. Same with division. If you're dividing two numbers with the square root there, you can break them up and play around with them that way. So it leaves you a little bit of room for maneuvering these types of expressions. So, for example, in this one, the square root of 45. This is not the most simplest way we could write a simple surd form, in its simple surd form. What we want to do is be able to split it up. And I've chosen 9 times 5. The reason I've chosen 9 times 5 is that 9 is a perfect square. And the square root of a perfect square gets you back to a whole number. Now, they're the only ones that will do it. So what I'm looking for when I try to simplify a surd form is their numbers that go into 45 that are, or whatever number I'm taking the surd of, that are perfect squares, because then I can start to simplify them. 2 root 6 is an entire surd. Well, again, 2 could be written as the square root of 4. And the square root of 4 times the square root of 6 gives me the square root of 24. Some manipulations as well here. Square root of 72, can I write that as x times the square root of 2? Well, I can manipulate it either way here, but notice I'm just trying to get back to a simple equation. Get rid of the square root. So x squared times 2 can be, that's what that one can be written as, which now I've got the square root of both of those. Well, what's under the square root signs must be equal. Comes down to x being equal to 6. Notice I won't get minus 6 there. We're dealing with positive numbers as well. 3 root 7, square root of x, so that could be written as 9 times square root of 9 times the square root of 7. Gives the square root of 63, which is equal to the square root of x, so x is 63. So that's how we simplify our surds there. Adding and subtracting surds. Now this is where it's a little bit harder. But if you think about it like in algebra or fractions, that we try and add and subtract like terms in algebra. So the same thing here. We try and add and subtract like surds. Instead of terms, put surds. So that's what we're trying to do there. Same with fractions. We try and add and subtract like denominators. So the same idea is how we work there. So proving that this can't work, it doesn't work like it does for multiplication. Square root of 36, square root of 64. Well, if you do that, that'd be 6 plus 8, which is 14. But 36 plus 64 is square root of 100, which is 10. Now 14 is not equal to 10. So that rule doesn't work. So you just can't add your surds like that. So that gives us a good indication of what not to do. So what we've got to try and do is break these up all the time and look for a common surd. When I try this one, I'd try and look at the smallest one first and try and get a surd there. Once I've broken square root of 8 up into 2 root 2, or square root of 4 times the square root of 2, I'm looking for, can I get 4 into all those, or also 2 into all those, and see what I get, so I can get a square root of 2. So I'm looking for the same surd each time. Once I've got one of them, do the others break down, because it wants us to simplify. So that's going to be a case of, that's what the problem wants, it's going to do. The same thing here, find the value of x. We need to get this one into one third, so they obviously will break down. 7's not going to break down anymore. So can I put 7 into 28? I can. That goes in 4 times. 7 goes into 63 9 times. So square root of 9 is 63. Square root of 4 is 2. So I'm able to break that down and be able to collect our my surds there to get 4 root 7 or 16. Square root of 4 is 16. So 16 times 7 gives me 116. So I'm able to get that value of x there. Finding the value here again, trying to simplify. There's the key. Is it's telling me to put into some number times root 3. So can 3 go into 48 and 75? Well, it can go into 48 16 times. So square root of 16 is 4. And they just happen to work out to be nice perfect squares. 3 goes into 75 25 times. So there's our 5 root 3. And then I'm able to collect and get 12 there. As we said, multiplication's pretty mundane. It's the more work you're going to do is for adding and subtracting. So multiplying, as we said, we can get all these rules. Remember, root 5 times root 5. Well, it's the same as saying that let's the square of root 5, which is going to be 5. So the other numbers multiply together. If our surds simplify like that, well and good. If not, then we break it down to our simplest surd that we can find, which is basically that there is no perfect squares that will go into it. So our further surd products here. So expanding it out. 3 times root 2 times the root 3. Again, we follow all our rules as we've done before. 2 times root 3 times root 3 gives us the 3. Looking at this one, if you can notice it's the difference of 2 squares, and this will come up in a minute again, then it makes life easier because you get square root of 5 times square root is 5. 3 3s are 9. So it's the same thing except it's just a different signs there, which we call the conjugates. Now we've used that word already this year, but the conjugates, and conjugates are really nice because it gives us the difference of 2 squares, turns something that was having irrational numbers in there to an answer that's going to be completely rational. It gets rid of those irrational numbers for us, and we'll talk about that in a minute, as I said. 2 root 7 minus 3 all squared. Again, use our rules we used in algebra, expand it out and clear them up. Now, the idea of rationalizing the denominator. As I just said, when we've got something like that where we've got rational numbers and we want to get rid of get something that is rational, we multiply conjugates because it comes down to the difference of 2 squares. And because you do that, because those terms being squared, they're going to end up with a rational answer, a minus b. So conjugate surds, when they multiply, always give a rational number, which is very helpful in what we want to do. Now, for our division, we didn't do much with division as such because it's pretty mundane. It doesn't do very much for us. What we really want to do is more doing the idea of rationalizing a denominator. So 5 on root 5. How do we rationalize our denominator there? Well, we multiply by root 5 on root 5, which is 1, and we're not changing the value of it. So root 5 times root 5 gives us the 5, and so they will start to cancel, and we get root 5 there. So we can do that with your index laws, or you can do it in the calculator to check that the validity of 5 over root 5 is equal to root 5. So same thing, this one, root 3 on root 2 multiplied by root 2 gives us a root 6 on 4. Our aim is to rationalize the denominator. Even if our denominator there is 1, that's fine, that's rational. 1's a rational number. Same thing with this one. This time it's a little bit harder because we've got 2 terms in the denominator. But as we just saw, multiplying by its conjugate allows us to get a rational number in the denominator, because the 5 times root 5 is 5. The root 3 times root 3 gives us the 3. And because it's the conjugate, we know because of our laws it gives us the difference of 2 squares. The 2 multiplies by the 5 and the root 3. And then we get the situation, well, that will give us 2. And our 2's will cancel. There's a common 2 up there. That will cancel, just give us the root 5 minus the root 3. Brings it down to its lowest terms. Root 7 minus root 2 in the denominator, we multiply by. root 7 plus root 2 because they're conjugates. But we've got to multiply by top and bottom because technically we can't change the value. That's got to be equal to 1. So again, that gives us the difference of 2 squares on the top, and then it's a perfect square up there. So root 7 all squared gives us 7. Then we've got the 2 times 2. Now there's an error there. We should have, that should be 4. That shouldn't be 7. And that should be 11. So, and then 2 times the root 7 gives us 4 root 7 there, using our expansion. And then this one here we've got, where we've got 5 plus 2 root 3, and we've got to multiply by the conjugate of 5 minus 2 root 3. Again, a little bit not too easy, but not overly hard, because once we realise we get the 5 times 5 is 25, 2 2s are 4 times the root 3. Now, major errors is going to be saying root 3 times root 3 is 9. Because we've said 5 times 5 and 2 times 2, the root 3 times root 3 is only 3, so that's where we get the 4 times root 3. So be really careful with that one. That's the major errors that occur. Expanding the 2, so we get our four terms up the top, then collect out any like surds or like terms. So 5 plus the 18, minus 2 minus 15, gives us the minus 17 there. So that's what we're looking at with our expansions there. And then the idea of equality of surd expressions. We sort of did this before, and this is just really manipulating our surd expressions to get rational parts that are equal and irrational parts. So the question you're going to see here is being able to go, well, if I've got that expansion, can I put it back into that form? And it's just a case of expanding it out, multiplying it out, and then collecting any like terms. So we get a rational part, must match up with the x, and an irrational part, because we've got a root 7, so that must be a root 12 for y. And that's all it is. It's just putting it in a particular form where a and b are rational numbers. So we're going to ignore the surd parts and then put it into that form. And you can see with this one here as well, we rationalise the denominator, so we get to 2. So that's really the way of writing there, a half times root 5 minus the half. So you can see that the a that was in front of the root 5 must be that half there. So that's why a is equal to a half. And b is the other number, the other rational number. It's not with the surd, so the b is equal to a half there because it's by itself. So it's just putting it into that form and doing a little bit of an extra manipulation with that work. So there's all the rules we follow with surds. Again, it should be only a review for you because you've done a lot of this work before, but we've got to make sure that, again, we get these right because they are going to come up in the rest of the course as we go through and be able to use exact values and exact forms of surds in solutions to other problems.